right, guys, here's our final lesson for probability. It's on dependent and independent events. So, what are independent events? Okay, independent events are, let me find a marker that works, two or more events that are unrelated to each other. Meaning the outcome of one is not going to affect the outcome of another. So like what I roll on a number cube is not going to affect at all what I flip on my penny. They're two completely unrelated events. And how do I find their probability? Well, I multiply each probability together. So if I was trying to find the probability of rolling a 4 and flipping a tails, I would say rolling a 4 is 1 out of 6, and flipping a tails is 1/2 or 1 out of 2, and I would multiply those together to get the answer of 1/12. So here's what we're going to do. We're going to practice our tree and sample space just one more time, but then we're going to use multiplication to check our answer. So it says, for the situation below, use a tree diagram to find the sample space and the number of possible outcomes. Then find the probability of the event occurring. Finally, check your answer using multiplication. So for an activity at school, Nolan had to spin each of the spinners below. What is the probability of spinning a red on spinner A and a blue on spinner B? So again, we're going to practice our trees again. So I'm going to say A and B. Spinner A and then spinner B. Okay, so what events can happen on spinner A? Well, I have 4 options: red, yellow, green, and blue. So I'm going to write R, Y, G, and B. So when I spin spinner A, I can land on one of those 4 things. And then when I spin spinner B, we can land on one of 3 things: blue, green, or red. So I'm going to make 3 branches coming off each, right? Blue, green, and red. Do it again. Blue, oops, I made an extra branch. Blue, green, and red. Blue, green, and red. Blue, green, and red. So in other words, no matter what I spin up here, down here for the second spin, I can land on blue, green, and red. So remember, this is my tree diagram to help organize my sample space. And my sample space is just a list of all the possible outcomes. So I could do red and a blue, red and then green, red and then red. Okay, now I'm done with the red tree, so now I'm going to go to the yellow tree. I could have spun a yellow and a blue, a yellow and a green, a yellow and then a red. Done with my yellow tree, so I'm going to go to my green tree. I could have done a green and then a blue, a green and then a green, a green and then a red. Okay, done with my green tree. Now let's do my blue tree. I could do blue and then a blue, blue and then green, blue and then red. Okay, this is my sample space. It's a list of all the possible outcomes. How many possible outcomes are there? If I count them all up, I find out there's 12 possible outcomes. And this one says specifically spinning a red on spinner A and a blue on spinner B. So R has to come first with B coming second. And when I look, there's only 1 out of 12 ways that would happen. So I have a 1 in 12 shot of spinning a red and then a blue. Now it says to check that using multiplication. So this is how I would do it. I would look at spinner A, and I would say, what's the probability of me spinning a blue? Or sorry, a red. It's red on spinner A. So what's the probability of me spinning a red? There's 1 out of 4 spaces on spinner A that are red. I'm going to write it over here, actually. Okay, and then it said spinner B, a blue. Okay, so I look. There's 1 out of 3 even spaces that are blue. So if I multiply these together, 1/4 times 1/3, do I get 1/12? Yes, I do, and that just means I did it right. So tree diagrams and sample space we're going to kind of go away from now. Now we're just going to focus more on the multiplication, which makes our lives a lot easier. So let's look at this next question. A game requires players to roll 2 standard number cubes to move the game pieces. What is the probability of rolling a 2 or 4 with the first cube and then a 5 on the second cube? So here I have 2 number cubes, and I'm going to roll them for a game. Saying on the first number cube, what's the probability of getting a 2 or a 4? And on the second number cube of me rolling a 5. So, okay, let's think about this one first. 2 or a 4. So there's 6 sides on my number cube, and 2 of them have either a 2 or a 4. And for this one, again, there's 6 sides on a number cube, and only one of them has a 5. So I'm going to multiply those numbers together to get my answer. Now, you can use your calculator to help you, and your calculator should put your answer in simplest form, or simplify first. 2 can go into 2 one time, and 2 can go into 6 3 times, and then we multiply across. So 1 times 1 is 1, and 6 times 3 is 18. It's probably actually faster to do it like that because it's pretty simple math. So 1 out of every 18 times I roll my dice, should I get a 2 or 4 on one of them? Sorry, and a 5 on the second. For these 2 questions, it says a penny is tossed and a number cube is rolled. Find each probability. All right, what's the probability of flipping a tails and a 3? So for tails, there's 1 out of the 2 sides of the coin that has tails. And then for a number cube, there's 1 out of the 6 sides that has a 3. So if I multiply those together, I find out I have a 1 in 12 chance of flipping a tails and rolling a 3. Let's try this one. The probability of flipping a heads and rolling an odd number. So heads, there's 2 sides of a coin and one of them is heads. And an odd number, there's 6 sides on a cube and 3 of them are odd, 1, 3, and 5. Okay, I could simplify this down to 1/2. So I have 1/2 times 1/2. So I have a 1 in 4 chance of flipping a heads and then rolling an odds. So this is called independent events. What happens to one has no effect on what happens to the other probability. But we do have events that are called dependent events. And that means when one event affects the outcome of another. So what are dependent events? They are when 2 or more events where the outcome of one event affects the outcome of another. And how do I find their probability? The same way. I find the probability of each and multiply. All right, now notice it says, be careful. When you have dependent events, the denominators will be different each time an event occurs. So I'll explain to you exactly why that happens here in a second. So it says, find the probability of the events occurring below using multiplication. There are 4 oranges, 7 bananas, and 5 apples in a fruit basket. Eric selects a piece of fruit at random, and then Tori selects a piece of fruit at random. What's the probability they're each going to pick an apple? 2 apples. All right, so first thing we have to do is figure out how many pieces of fruit are in the fruit basket. So picture a lunch line. You're going through the lunch line. You have your tray of fruit. This is what's on the tray. There's 4 plus 7 is 11, plus 5 is 16. So I'm going to put the 16 up here. There's 16 pieces of fruit in my basket. So when Eric goes through, there are 5 apples out of the 16 pieces of fruit. So there's a 5 out of 16 chance that Eric's going to select an apple at random. Okay. Now, Eric selected his apple and he walks away with it. How many pieces of fruit are left in the basket now? Well, now there's 15. So 15 is our denominator. That's what this means. When you have dependent events, the denominators will be different each time an event occurs because something has been taken out. Okay, here we go. How many apples then are left? Well, there were 5 apples, but Eric took one, so now there's only 4 apples. So now there's a 4 in 15 chance that Tori's going to pick an apple. To figure out how the probability of both of them picking an apple, then I have to multiply. So let's do some cross simplification. This is going to become a 1, and this is going to become a 3. This will become a 1, and this will become a 4. And if I multiply across, I know there's a 1 in 12 chance that both Tori and Eric are going to pick an apple from the fruit basket. Okay, let's try again. So all the fruits back in. What's the probability of a banana and then an orange? So 16 pieces of fruit. Eric's going to pick a banana. There's 7 bananas, so 7 out of 16 for Eric. Now, Eric took his banana and it's gone, so now there's only 15 pieces of fruit. Now, since he picked a banana, that has no bearing on an orange, so there's still 4 oranges in the basket, so I can still use that 4. There's 4, but the only thing that changed it now is my denominator. It's 15 pieces of fruit now. So there's a little bit of simplification I could do here with my 4 and my 16. Now I'm going to multiply across. 7 times 1 is 7, and 4 times 15 is 60. So 7 out of 60 times, Eric will choose a banana, and Tori will choose an orange. So maybe it would be a good idea to pause it and then try and answer these next 2, and then start it and see how you did. All right, pause me. All right, let's see how you did. So an orange and then an apple. So 16 pieces of fruit, 4 of them are oranges, times, now that an orange is gone, there's only 15 pieces of fruit, and there's 5 apples still. Okay, both of these could actually be simplified. I could change 4/16 to 1/4, and I could change 5/15 to 1/3. So I'm going to rewrite this problem right here because it makes it easier for me to multiply and find out there's a 1 in 12 chance that someone's going to choose an orange and then someone's going to choose an apple. And then finally, the probability of 2 oranges and then a banana. So again, 16 pieces of fruit. There's an orange, so 4 out of 16. Now, Tori's going to come through, and now there's only 15 pieces of fruit. But remember, Eric already picked an orange, so now there's only 3 oranges left. And now Julie is going to come through, and there's only 14 pieces in the basket for her, and she's going to pick a banana. There's still 7 bananas in there, though, so it's going to be 7 out of 14. Now, again, each of these can be simplified, so I'm going to write them again. 4/16 can be 1/4. 3/15 can be simplified to 1/5. And 7/14 can be simplified to 1/2. So when I multiply these across, 1 times 1 times 1 is 1. 4 times 5 is 20, and 20 times 2 is, I was going to write down 20, is 40. So 1/40. Okay, let's try it again in a different scenario. So cards labeled 5, 6, 7, 8, and 9 are in a stack. A card is drawn and not replaced. This not replaced means that it gets taken out and it does not go back in the stack. Then a second card is drawn at random. Find the probability of drawing 2 even numbers. All right, well, how many cards are in my stack? 1, 2, 3, 4, 5. So there's 5 cards in my stack. And how many of them are even? 6 and 8 are my only even numbers. So there's 2 out of 5 chance that the first time I'm going to draw an even number. Times, let's talk about the second time. Because I drew a number and did not replace it, that means, let's say I drew the first time and I drew an 8. That means the 8 is gone, leaving me only 4 cards left. And now only one of them is an even. So my second time, it's going to be a 1 out of 4 chance I draw an even. So I can simplify a little bit here with the 2 and the 4. And I would find out that I have a 1 in 10 shot of getting 2 even numbers. One more thing. Maddie is packing for a trip. In her closet, there are 3 red, 4 purple, 2 green, and 2 blue shirts. She randomly selects 2 of them. Find each probability. Okay, so Maddie's packing her bag for a trip. She's got all of these shirts. Let's see how many she has. So 3 plus 4 is 7, plus 2 is 9, plus 2 is 11. So she has 11 shirts in her closet to pick for, and she's just randomly going to pick 2 of them out, or 2 of them in her drawer, however you want to think of it. So what's the probability she's going to pick a red and then a red? So the first time, there are 3 red shirts out of the 11 that are in her drawer. Okay, so she picked out a red shirt. She's put it in her bag. Now she's going to try pulling out another shirt. Now there's only 10 shirts because 1 shirt's already in her bag. And how many left are red? Well, she's already used one of the red ones, so now there's only 2 red ones in her bag. I can simplify a little bit here. 2/10 can be simplified to 1/5. Now I'm going to multiply across. 3 times 1 is 3, and 11 times 5 is 55. So there's a 3 and 55 shot that she's going to pick out both red shirts. Okay, probability of purple and blue. So again, all the shirts are back in the drawer. She's got 11 shirts. And let's see how many are purple. 4 purple times. So she picked out a purple shirt and it's gone. It's in her bag, which means now there's only 10 shirts to choose from. And how many of them are blue? She didn't touch a purple one, so there's still the 2 blue that are in there. Well, let's simplify. So 2/10 can become 1/5. And then I multiply across. 4 times 1 is 4, and 11 times 5 is 55. So there, 4 out of every 55 times she randomly selects shirts would she pick a purple and a blue. Okay, so how about you pause and try the next 2. All right, let's see how you did. So for red, there was 11 shirts to choose from, and 3 of them are red. For purple, she has 4 purple shirts, but there's only 10 of them that are left. I'm going to simplify here, making this 2/5. And 3 times 2 is 6. And 11 times 5 is 55. So 6 out of every 55 times she picks random shirts, she would pick a red and a purple. And the last one is a green and a green. Okay, so 11 shirts in her closet. 2 of them are green. Times. Now she only has 10 shirts in her closet, and now only 1 of them is green because 1's been put in her bag. I could simplify a little bit here with my 2 and my 10. 1 times 1 is 1, and 11 times 5 is 55. So we would guess that 1 out of every 55 times she picked shirts would she pull 2 green shirts.